Hi everyone. I think let's start. Yes, today I will talk about that NNVM and the TVM intermediate representation stack for deep learning, and the OpenCL support in this stack. First of all, I will spend several minutes to give some brief introduction about OpenCL, and then I will move to the major part about NVM and TVM. After that, I will talk a little bit about current status for this part. I think people here may already know what OpenCL is. So it is an open computing language maintained by Cronus organization. So it is cross-platform, heterogeneous, and parallel programming standard. Supports CPU, GPU, DSP, FPGA, and other accelerators if needed. So the first version was released in 2008. And the latest version is OpenCL 2.2, which was released in May last year. And there is some discussions and the trend to merge the OpenCL support together with Vulkan, because Vulkan has compute support already in the designs or in the spec definitions. So there is some trend on this, but we do still need some time to achieve that. So we can see that a lot of vendors already have OpenCL compatible implementations for CPU, GPU, for FPGA, DSP. So I think for this session, we can probably focus on the mobile GPU part, because this NNVM TVM part we are going to discuss here is to using these mobile GPUs for deep learning inference on edge devices. Okay, so a typical OpenCL application usually consists of a host program and a device program. So for host programs, host APIs are defined for platform device management, context management, memory management, and the command queue and scheduling, etc. So, and a device kernel is the program to run on the heterogeneous devices or accelerators. So for earlier OpenCL versions, only OpenCL C type is supported, which is a C99 subset with extensions for parallelism. And for OpenCL 2.2, OpenCL C++ was introduced. And in OpenCL 2.0, on-device dispatch support was introduced. So to make the device kernel run on the GPU devices or other accelerators, some compiler is needed to convert the device kernel to a device executable code. So I also mentioned the SPARE here. SPARE is a standard portable intermediate representation, and the specification is also defined by Cronus with its members. And the most recent version is SPARE V, which is a cross-API standard introduced in OpenCL 2.1. So this is very important because SPARE V can be some kind of OpenCL compiler support, and which is very important for the convergence of OpenCL and Vulkan. Okay, so for the execution model, so there are different hardware implementations for parallel computing. For example, SIMD, single instruction multiple data. So it is used by neon instructions, right, for x86, it is SSE or AVX, right? So some Mali GPU also support async parallel computing. So there is also a VLRW, right? This is also used by Mali. So and for the desktop GPUs, for example, NVIDIA graphic cards, AMD graphic cards, they usually use SIMD. So it is single instruction, multiple threads. Yes, and we have some other calling or we call warps or waveforms. So so OpenCL abstract the date parallelism into any range or index space, work group, work item. Each work item is the minimum kernel execution unit. So every work group can have multiple work items. And the index space can have multiple work groups. So this is the basic mechanism for the parallel computing with OpenCL. So, and if you want to run a kernel, you can call the CLINQ and range kernel for the execution on each work item. Okay, so there is also a different memory type defined by OpenCL, and for example, the local memory is only accessible to work items in the same work group. And for private memory, it is only accessible to a single work item. For OpenCL 2.0, the shared virtual memory mechanism is introduced. So yeah, so I tried to be quick about OpenCL introduction. I think because the focus of this session is about NNVM and TVM. So for the AI ecosystem, and just as we discussed in the BOF this morning, so it is very fragmented. So there are multiple frameworks with different front-end interfaces and back-end implementations. So for application algorithm developers, it is difficult to switch between frameworks. And for framework developers, they need to maintain different backends for various accelerators. And for the chip vendors, they needed to support multiple frameworks with duplicated efforts. So they needed to enable hardware in different frameworks with similar effort. It is a headache, you know. So NNVM and TVM was introduced to address above challenges. NNVM, or neural network virtual machine, is a computation graph IR stack. So the computation graphs are standardized, optimized for models from different frameworks. The NNVM compiler leverages the TVM backend implementations. So for each vendor, they needed to enable the hardware in TVM and do the optimizations. They don't need to do yet for each framework if we can have all the framework models supported by NNVM. So TVM is the Tensor IR stack. It is under the NNVM. It is mainly for operator level, not graph level. So it was inspired by Harley IR, and it is a DO-pack compatible. So it already has multiple language support, for example, C++, Python, Java, JavaScript. So to support the inference acceleration on mobile GPUs, I think at this moment, OpenCL is one prop option. So if we can have OpenCL support well, we can leverage the power of a GPU in this area. Okay, so this diagram try to explain the compilation stack. So we know there are a lot of deep learning frameworks in the world already, right? So and there are a lot of model Zhou from each framework containing the pre-trained models. So NNVM provide different front ends to translate the pre-trained models into NNVM symbol. So it is an NNVM representation of the model. So it has a MXNet front end, right? It has ONNX front end. ONNX is a standard open exchange format initiated by Microsoft and Facebook. So, and it is more framework support ONNX now. So Keras front end. So Keras is maybe Python library with a unified APIs, but on the back end it can support different frameworks. For example, TensorFlow, Caffe, and it also has a Core ML front end support. Core ML is a specification from Apple, right? So with this translation, so we can call NNVM compiler to do the graph optimizations, to do the operate optimizations, and NNVM compiler will call TVM to generate the model, or we call TVM model. I will talk about it later. And this model can be run on the embedded devices or edge devices directly. So TVM, there are major two parts in my understanding. So TOPI, it is tensor operator inventory. It mainly defines the operators, defines the schedule primitives, and have optimizations for different backends or different accelerators. So it have CUDA optimization, LocM optimization. LocM is for the AMD LocM stack. So Mali optimization, which was added recently, and Raspbian optimization, it is just for the CPU optimization. So for the code generator, it can support a lot of backend now. For example, ALVM, CUDA, Metal, OpenCL, right? So OpenCL will be talked here. So there are several important design concepts in TVM. So one is the packed function. It is type erase function, and some restricted argument types are supported for simplicity. And so it is by both the compilation stack and the deployment stack. And so for example, here there's a global function registry maintained in the C++ runtime. So you can call from the Python into C++, call the packed function defined in C++ directory. And in the C++ runtime, you can call the Python function directory registered to this registry. Another thing is runtime device API. So the device API is mainly for the memory management support. So for OpenCL support, we needed to implement these functions or APIs with the OpenCL cores. Another important concept of TVM is the TVM module. So TVM module is a runtime container packed functions generated by TVM. So the driver rules are implemented in C++ and exposed to users such as Python by runtime API. And there are several important functions defined. Get function. So we can get the packed function from the TVM model by the name string. So an import. So we can import another module into the model. For example, OpenCL module is imported into the host module. Load from file, load the host function module from file. So yes, this is a concept of a module. So there is some internal container module. It's called a module node. So for module node, we need to implement OpenCL module node for OpenCL implementation or OpenCL support. So this OpenCL module node handles the execution of OpenCL kernels in one OpenCL program. Okay, so this is the TVM TOPI. So for the TOPI part, I think the Python decorate, because the TOPI implementation is mostly in Python. So the Python decorator mechanism is used, and it is very flexible, and you can define the generic function, and this generic function has a dispatch dictionary. You can register different functions to this dictionary for the same operation. For example, for the convolution operator, you can register CUDA implementation, you can register OpenCL implementation, so it is very helpful. And Python context switch, so we can use the with keyword to do the context switch. For OpenCL support, so OpenCL reuses a log-m schedule. So because the log-m part is maybe some kind of OpenCL implementation. And log-m set both log-m and GPU keys. Just as I mentioned before, the keys are used to find the correct function. So, and the CUDA target registers many functions with CUDA and GPU keys. So, for OpenCL, since it reuses log-m, so it can, if the operator is not defined by defined specifically for log-m, the CUDA implementations were used. Because if the log-m key is not found, the GPU key will be searched. Okay, so Mali target registers some additional functions specific for Mali. OpenCL code generator. So lower function is the final R representation before code gen. So these lowered functions is transformed to OpenCL device code by the OpenCL code generator. This OpenCL code generator will handle the storage scope and sync, handle thread index, handle type handling, the vector support, right? So, and then the OpenCL device code is transformed to the TVM module by the OpenCL module create. The TVM module is what was needed to do the real inference on the device side. Okay, so this is the TVM deployment stack. With the orange block, so these are the output from the compilation stack. So you can get it on the device natively. You can also do the cross compilation on the host side and upload it to the device. In this case, you just need to have the runtime library on the device for the inference. And upload the model, the TVM modules and the parameters on the device. And you can call set import to do the inference and call get output to get a result. One thing to note is that if you want to do the remote deployment, the OpenCL support should also be enabled in host side. Okay, so there are some examples about this OpenCL support. So I maintain several scripts for this as some examples. For example, if we want to do simple multiple and add operation, you can do it locally on the ARM device. You can also cross-compile it on host side and upload the TVM module and the related files to the device and do the inference on the device side. And there's some example to do the inference with the ResNet 18 model. So it is an end-to-end inference, not just a simple operation. So if you have interest, you can click the link and try it. So I will not go into details about this part because time limited. Yeah, so I will talk a little bit about current status. So this is an optimization done by Lian Ming from Shanghai Jiao Tong University on the Firefly RK339 platform. I also did some verification on the log 96096 board this week. So basically the results are similar. So the data here, for the diagram here, the ARM computer library version 17.12 was used for comparison. Of course, there may be some changes with their new releases for some optimization in the library. And one thing to note is that for VGG16 model, it requires a lot of memory to make it work. So I think 4 gig memory is a recommended configuration. If you only have 2 gigabyte memory, I don't think it's suitable for such kind of work. Okay, so we can see that the TVM performance is very good comparing to CPU and the ACL. Okay, so I put a link here about the TVM roadmap. So this, because TVM is a community project, so everybody is interested in it, you can join. So specifically for OpenCL, I think there are still several things we probably need to do, because currently the platforms supported by TVM are quite limited. If you have interest, we can probably try it on other platforms with OpenCL support, right? I did some basic work on the Bubblegum 96 platform, which is OpenCL 1.2 compliant. But it looked like we needed to implement some specific Power VR schedule to address some problems, because the GPU hardware configurations are different between Mali and Power VR. And we have some new 96 boards announced this week, right? So, for example, the Dragon Board 820 and the HKG18-417, right? And maybe the Ultra 96. It is a FPGA board. If you can get FPGA supported by TVM, that will be great. So, and some other things, for ARM computer library, I'm thinking if it is possible to integrate this library into TVM directly, because now with TVM, the ARM Mali optimizations is done in Python level, and the OpenCL algorithms are applied directly. For example, to support the image to column algorithm. If we can integrate OpenCL into this library, we can leverage mostly the effort from ARM. And we probably need to validate more frameworks and models with NNVM TVM, because quite limited models are verified so far. And then maybe there are some different parameters, different optimizations. I think there's still a lot of work to do. But I think the architecture is very flexible to solve some kind of fragmentation in the ecosystem. But we need the whole community to support this or to buy in this. Yeah. So, and maybe we can also think about some OpenCL 2.0 related optimization for the boards supporting OpenCL 2.0. Okay. So I think that's all for my slides. Any questions? Okay. So I think if I have any questions after this week, or maybe you can try the TVM, I'm open for the discussion. Yeah, thank you everybody.